So we are going to go to our last presentation from FIU. Of course, it's not our last for today for FIU. It's on integrated flood and socio-environmental risk analysis for prioritizing ABC activities. Dr. Ali Ebrahimian from our Civil and Environmental Engineering Department is going to present that. Dr. Ebrahimian.
Good morning, everyone, and thank you for listening to my presentation. Many thanks to the ABC UTC administrators for providing the chance for interdisciplinary projects like this to be included in the program. Today, I'm going to be talking about this project, which is basically about the development of a risk-based multi-criteria decision support tool, which in this application, I'm talking about using that tool for the prioritization of accelerated bridge construction rehabilitation projects. This project is being done by my PhD student, Nasim Mohammadi Azar. So most of the credit, I believe, goes to her. And I believe that we started this project last year about this time, so we are currently in the final steps of the project, and I'm really excited to present our sort of preliminary analysis and our full procedure or methodology today. So I'm not sure if you remember this background because I've already presented that in the other research days in the previous year. But the first question is why we are considering flood and socio-environmental factors in addition to structural factors for decision making about which project to choose for rehabilitation, or basically for ABC rehabilitation. So in terms of flood, basically flood can impact the construction speed. And on the other hand, if we use ABC, we actually have the chance to minimize the need for temporary flood diversions during the construction phase. So that's a benefit that ABC can provide in terms of flooding factors. And then in terms of social factors, basically social factors in one hand can affect the construction speed. So you can consider working in a highly populated area, in a high density urban area, or in a high crime rate area, and you can expect some interruptions into the construction process. On the other hand, if we use ABC project, we are actually reducing the construction time, and we can expect to have more public consent due to that reduced project time, which is a big thing in terms of the general success of the project. And at the same time, by improving social functions in urban communities, we are contributing to faster revitalization of some of the underserved communities, some of the highly populated urban areas, such as high crime rate neighborhoods and things like that. So in this way, we are basically adding social equity into infrastructure planning, and this way we are kind of talking about the other benefits that an ABC project can provide. And in terms of environmental factors, we can quickly say some factors such as, for example, high temperatures or bad air quality are basically a threat to our workforce health, and they can impact construction speed. And at the same time, by having ABC processes, we are reducing the exposure of our workforce to those threats, and we are actually contributing to accelerated environmental benefits for our urban communities. The other quick question, but very important one, is why do we need a multi-criteria decision support tool? Well, the answer is basically according to FHWA, more than 25% of all the bridges in the country need some sort of rehabilitation or repair. So that's the first thing. And on the other hand, we always have limited budget. So this is basically a tool that can assist FDOTs as our decision makers for selecting the project that are in higher risk, or they can provide higher benefits. So in this project, basically our objective is to develop a risk-based, spatial, multi-criterion and multi-stakeholder decision analysis framework to prioritize the accelerated upgrade or accelerated repair projects. And again, in this project, in addition to structural and traffic conditions that traditionally all the state DOTs consider for selecting the rehabilitation projects, we are also incorporating flood and socio-environmental factors into the process. So the tool that we are developing should be simple. We understand that it should be simple enough to be able to use that in real project. At the same time, it should be systematic or adjustable to be able to be used in different applications in different geographic regions. It should be GIS based to capture the spatial aspects of flood and socio-environmental factors. We'll be trying to use the readily available data as much as possible to increase the applicability of the tool to all the projects. And then last but not least, the tool should be able to capable of addressing group decision making, because a lot of times we have multiple decision makers in a problem, and we should be able to consider their opinions, their preferences in the decision making process. So we selected the urban areas of Miami-Dade County as our case study here, not just before FIU is located at Miami-Dade County, but that's basically because of the unique socio-demographic characteristics of Miami-Dade County in Southeast Florida, because that's basically the county with highest population, more than 2.7 million people in Florida, and basically more than 70% of the population include Hispanic or Latino groups, and including a lot of underserved communities. So this flowchart shows the general methodology of this project. I understand this is a little busy, but I'll make sure to make it easy for you to understand. So if you look at the left-hand side of this flowchart here, we are basically collecting physical data that are related to flood factors, social data, and environmental data. And based on all those data layers, GIS data, we are creating some vulnerability maps. And finally, we combine or we integrate all those vulnerability maps to create a vulnerability maps in terms of our urban area. So we are not talking about the bridges yet, but when we go to the right-hand side of this flowchart, we are basically talking about the traditional factors that, for example, state DOTs have been using in terms of traffic data in bridge locations, and also the structural conditions of the bridges. And again, we create another vulnerability map just based on the structural condition and traffic condition of the bridges. And finally, we integrated those maps to come up with a final risk map. And this is basically the final product of this tool that gives us a risk level for each individual bridge, that the risk level could be from very low to very high. And that is the tool, and that is the product that can help our decision makers or they can inform the decisions by state DOTs in terms of selecting the projects. So in terms of environmental data, we looked at temperature and air quality. For physical or fraud related data, we tried different data, but we finally ended up with using 8 different data layers, as you see here, from hydrologic soil groups and distance from canals, depth to water table, imperviousness, and so on. And for example, the imperviousness, the higher the imperviousness, the higher the potential for flooding. Or since Miami-Dade County is kind of a coastal area, so we did consider hurricane evacuation zone in this decision-making tool. So that means that if a bridge is located in an hurricane evacuation zone, that specific bridge should get more attention. And in terms of social data, we ended up using 6 different data, as you see here. And these are the data that can actually help us with the incorporation of social equity into our problem. So we are looking at, for example, the population density. If a bridge is located in a highly populated area, that bridge should get more attention. And then land use is important. If the bridge is located in a suburb or in a very uh, like suburb area, residential area compared to a downtown area with a lot of people using that. If it's located in a low income neighborhood or high crime neighborhood. So these are the factors that we considered in this decision making tool. And again, these are to include social equity into decision making planning. The next step for our study was to reclassify each of these data layers to assign 5 different vulnerability classes, as you see here. So let me use my laser point here. So these are the 5 vulnerability classes from very low to very high. And for example, in terms of hydrologic soil group, this is the classification from USGS, and the soils in group A have more infiltration rates or low flood potential. So but since the flood potential is low, they are assigned to very low vulnerability. And on the other hand, the D soils are in opposite, and they get a very high vulnerability class. Same thing with other data. So for saving the time, I'm not presenting all of our classification methods, but instead I'm using our individual data. So this is the physical maps that we created. After that, reclassifying and assigning the different vulnerability classes. So these are all in terms of flood related data. And then at the next step, we had to integrate all those physical maps, and we used one of the simplest multi-criteria decision-making methods, which is called simple additive weighting method, to integrate those maps. So what you see here is the integrated flood-related map, which is part of our decision-making method. We followed the same procedure for our social data, and these are the individual layers after reclassification for our social data. You see, for example, income, crime rate, and so on. So same thing, we had to do an integration. So this is the integrated social vulnerability map with 5 different vulnerability classes from very low to very high, as you see here. And we did the same procedure to our environmental data. We used nitrogen dioxide and temperature, and we created our environmental vulnerability map similar to the other maps. So at this point, we are done with our left-hand side of our flow chart here. So we are now about to think about the traffic data and bridge data about each bridge. So the traffic data that we ended up using here was the average daily traffic and car crash density in our data. So you're familiar with the average daily traffic, and the car crash density was the number of crashes for the total number of cars driving over 1,000 miles of a road daytime. And excuse me, the bridge data, again, we tried to use the readily available data, or we tried to use the national databases in order to extend the applicability of the method to all the geographic locations. So we use the age of bridges as a proxy for their structural condition. So the older the bridge, the higher the vulnerability. We use an scour index from the national bridge inventory that is a score between 0 to 9, and for example, if that's between 0 and 3, the scour condition is critical, and as it goes higher it gets better. And finally, we use the sufficiency rate again from FHWA, and that's part of the way that FHWA basically allocates fund to state DOTs, and we use that as a proxy for structural condition of the bridges. So you see the individual maps for ADT and car crash in our case study area. And similarly to the other maps, we created the integrated traffic map for our bridges, and the difference here is that we do have point data in this map, and each point is a bridge in our study area. Same thing with the bridge maps. This is, for example, the age of the bridges and the cover index and sufficiency rate. And this is how we integrated all of our bridge related data, and again created this map. So to give you some hint is, if we didn't want to use the social and environmental data and even the traffic data, this map could be one that could be used for the decision making for selecting the project, because this is only based on the structural condition of the bridges. Okay, so in the next step, we do have all the integrated maps from flood-related, environmental and social, and from the traffic and structural conditions of the bridges. So we have another step before going to our final product. So we need to create an integrated vulnerability map based on all the environmental, physical, and social factors. And we are also creating another integrated vulnerability map based on all the traffic and bridge conditions. So this is basically the vulnerability map for urban areas based on physical, social, and environmental maps. And you see the 5 different vulnerability levels in urban areas. Again, this is for urban areas, so this is not a point layer. This is basically this gives you an idea of the vulnerability level for different urban areas, which are the bridge locations. But this one is an integrated vulnerability map for each bridge. So we have point data here, and these are the vulnerability map for each bridge. For example, the red one is the very high vulnerability, so they should get more attention in terms of rehabilitation or repair. However, if we want to integrate or combine the socio-environmental factors with the structural factors and traffic factors, this gives us basically the final product of this method, which is an integrated risk map. And this is basically the map that we were looking for in this project. And as you see here, we do have clear differentiation between the vulnerability levels for each project here. So each circle here is an individual bridge in our study area. And from this map, for example, I can see that the bridge is located in I-95 here, or this one I think is US 27 or Okeechobee Road. These are kind of the higher risk maps that should be selected first. However, one thing to consider here is that in this process, so far we have considered equal weights for all the social, environmental, and physical and structural data that we have been using for this decision making. And obviously, the relative weights of each data layer may be different for our decision makers, but the good news is the tool is able to consider that different weights. So if you're able to extract the preferences of our decision makers, we can apply that to the method, and we can revise this tool to consider that relative weights and to revise this final product here. Okay, so
Dr. Ebrahimian, can you please wrap up in a
yes,
minute?
that was basically my final slide. And with that, I would like to thank the ABC UTC again for providing this opportunity, and also thank you for listening to my presentation. And with that, I take any questions or comments.
Thank you very much, Dr. Ebrahimian. I think we are giving a little time to next presenter to log in. Looks like can be like some technical issues, but that gives us that's a good thing. So it gives us a little time to ask. We had a couple of questions coming in.
Sure, great.
The first question is asking, I guess I see, because you mentioned weights. The question is asking, is there any procedure for determining relative weights of the criteria?
Well, I believe that's a very important question for any decision support tool, because at the end of the day, the relative weights of criteria or decision criteria should be determined by the decision makers. So the first problem is, who is our decision maker, or who are our decision makers? And once we identified our decision makers, we should able to have a method or methodology to extract the weights or to get the weights from them. Sometimes they are eager to participate in this process. Sometimes it's a little difficult, but I personally have the experience of developing methods based on, for example, analytical hierarchy process or AHP. So we just, create a procedure to ask several questions from the decision makers, and from that we can extract the relative weights of criteria, and we can apply that to our decision making process.
Thank you very much.